problem for you today that was the last problem from a number in a number theory book. It was, like the last problem, number 50. Usually those are harder than the beginning problems. So this is from an elementary number theory course. And we're supposed to prove a result that if n has a certain property, namely that if n is a prime factor of n, and if also n squared is a prime factor of n, then it can be written as the product of a square and a cube. Okay. Now, what I did is I started with this perfect square case. And no, folks, in a perfect square, if you do the prime factorization of a perfect square, all of these j sub i's, all of these exponents have to be even. Okay. Now, you don't really have to know that. Case one is easy. If n is a perfect square, you can write it as, by definition, k squared times 1 cubed. So we're getting off kind of easy there. We get the 2 and the 3 just like the result wants, okay? Now, case 2 is a little different. Case 2 is a little bit different. If it's not a perfect square, that implies that at least one of the j sub i's is going to be odd. And the reason is that p squared definitely divides p cubed, right? Okay, p squared is a divisor of p cubed. Okay, and then, but it's not the case, and this is clear, but I think it's worth writing it down. P squared does not divide p. Okay, and I'll just put the little slash through here to negate the division operation there. All right, so that's why we have to start at 3. Okay, now at least 1. Now it could be multiple, and the result down here will prove that, but this is the case if we have at least one of the j's is odd, greater than or equal to 3. Now I just positioned it right here, did it in red so we could all follow it, including me. All right, but you see, since an odd number has this representation as 2r plus 1, okay? Now, y'all, we're assuming the rest of these j sub i's are even, because that was the, in case 1, all the j sub i's are going to be even. So we have to produce a non-perfect square, which can only happen if at least one of the j sub i's is odd. Okay. So now here's where all the work happened right here. This is the beauty. This is what it stumped me for the longest time. Just properties of exponents says that pi raised to the 3rd power times p sub I times this even number. If you do your laws of exponents, this would be 2r minus 2. If you add 3 to minus 2, you get the plus 1 you see over here. Isn't that cool? And so just like that, we have our cubic that we're looking for. We have something cubed, which is all we needed, right? We have something cubed, which is all we needed up here. It was just 1 cube, which is trivial. But in general, we just want something cubed that is an integer, all right? And of course, this is even right here, right? So you see all of this is an even entity. All of the rest of these are even, the exponents are even. And so what we have here is an integer cubed times a bunch of integers squared, which is an integer cubed times an integer squared. Now, if that's too much talking, here's a concrete example. I don't even know what this number is equal to, but if we start out with 3 squared, 5 to the 7th, 11 to the 6th, a large number, of course, you can rewrite all the squareds like this, right? You can write 3 squared, 11 cubed is 11 to the 6th. So this first piece right here handles 3 squared and 11 to the 6th, right? Okay. Now, I've split up, and this is exactly what this is saying right here. This, if you take a look, is this part right here is exactly this guy right here with r equals to 3. Okay, with r equals to, is that right? Yeah, r equals 3. Let me go ahead and write that in, because this is really the crux of the proof that makes it work. And if this happened, if all the others were odd too, you would still get what you wanted, because you would still have a prime cubed times a prime raised to a bunch of primes raised to even powers. Okay, so r equals 3 is this case right here. Now, and you see it all just works out nicely. You bring the 5 to the 4th back to the inside to get 5 squared. And so you see we do get an integer squared times an integer cubed. And we've handled a number, these are mutually exclusive cases here. A number is either a perfect square or it's not a perfect square. So there's nothing getting left out here, no law of the excluded middle or anything like that going on. Okay, so y'all, hope you like that. This is a concrete example that doesn't constitute a proof, but I don't see anything wrong with this proof. And since it was supposed to be a hard problem, I was wanting to check with you guys to see what you thought. Thanks for viewing.